Ah, gotcha. Well, good afternoon, everyone. I hope that you've had a good day and actually a good week. We would like to thank you for coming to Propulsion Energy 2014, and actually want to make an announcement. We mentioned this on Monday, but I think it's worth mentioning again that we're actually celebrating with this conference the 50th gathering of this community, of the Propulsion community. So I think that just is a spectacular anniversary. You guys owe yourselves a round of applause. So. And so happy birthday, everybody. And we're looking forward to the next 50 years of gathering together as a community. We've had more than 1,200 people attend this week. And you know, we've had some great conversations around propulsion and energy today, manufacturing. We're really looking forward to the panel that's getting ready to start. And I'm pretty confident that we'll all be leaving Cleveland having learned something, hopefully had a chance to visit with old friends, had a chance to meet at least the 5 new people that I challenged you with earlier in the week. We've had more than 600 paper presentations with 20 technical tracks. So there certainly has been tons of information to take in and learn. And again, we appreciate, you know, everybody participating in the forums. We all know how important these kind of gatherings are that allows our community to come together across all of the sectors of the aerospace profession and talk about what's going on. And, you know, and as you know, we do some really cool stuff, and it's really great to come together and see all of the different kinds of activities going on and spark new ideas for where we can go next. We have a couple of things, just final thank you to our sponsors, GE, NASA, Lockheed Martin, as well as Dunmore, Jacobs, Ohio Aerospace Institute, Sarah Lobo, Southwest Research Institute, United Launch Alliance, IEEE, INCOSI, and our media sponsor, Space News. We really do appreciate that support. A couple of housekeeping items. First of all, someone left a black portfolio binder in the lunchroom, so I will have it here in the front row, and we're going to take it over into the office in room 18. So if you hear of somebody who's lost a portfolio, let us know. There's a bunch of different cards in here, so it's hard to say which card is the owner's card. So clearly this person's met a lot of new people, but we'll have that for that person. And of course, we have microphones in the center aisle for the questions and answers after the panel discussion. So to get us started, I'd like to introduce Christine Furstos from Global. She's the Global Technology Director, Manufacturing Materials Technologies at GE Global Research, and I will turn the floor over to you, Christine.
Thank you, Sandra. All right, good morning, or good afternoon, everybody. I want to just take a few moments before we start our panel discussion, and I think you'll be so thrilled that you joined us today because we have quite an esteemed panel. I'll be introducing them in just a moment. But you know, talk about manufacturing at an aerospace, propulsion, and energy conference is a little bit different. So I want to set the stage to begin to talk about why manufacturing is as important an aspect as any other at this conference.
Manufacturing is moving forward. It's the dawn of advanced manufacturing. It's forward thinking, forward moving. It's real progress. Ideas at work that can be put to work. It's know-how. It's wonder. It's scale. Advanced manufacturing. Developing material science, innovating and creating opportunities with the industrial internet. It's embracing a new way of working, a new standard of efficiencies, from top to bottom, from supply to product, reimagining the workforce with a new, more powerful set of skills. It's a commitment to train people to make new things in a new way, so we can all work better. Advanced manufacturing is happening now. It's a reinvestment, a revitalization in industry, in jobs, in economies, an economic engine that's going to move all of us forward.
I hope that gets you as excited as it gets me, and it is something we put together for GE because we are dedicated, but as you'll hear from my 4 panelists today, every company is dedicating themselves to this. Every company is understanding what advanced manufacturing means to their business. And so today, You're going to hear from 4 different users. You're going to hear why manufacturing opens up new solutions. And why are we doing that? Because manufacturing is evolving. More than ever, hardware is meeting software. It's not a hardware type of world where software is just something we do before. It's part of everything we do, whether it's design, the two meeting, whether it's during the manufacturing cycle, or whether it's during the life cycle. More and more you'll hear from our panelists how hardware does meet software. And with today's world, with everyone being able to communicate more collaborations than ever before, the maker movement, we need to embrace this. Our community tends to be very conservative for all the right reasons, for safety, for reliability, for predictability. But how do we embrace what people are doing today with new ideas on manufacturing, new ideas on materials? How do we move that forward? And then finally, more and more, it is becoming a democratization of manufacturing. Small and medium enterprises entering into the stream. The need to build more ecosystems. Again, how does our community start to embrace this? Well, why is this happening now? These physical and digital worlds are converging. I just mentioned hardware meets software, but more and more we're trying to move with speed. We're trying to get more information early. We're trying to understand performance before we have to build the final product. We need agile manufacturing type technologies to get us parts, get us fast, be able to integrate with the design, and we need to build these new ecosystems. All the new players that we have out there today, all the new community that want to be a part of this, that's why today is the time. Because it can transform the entire supply chain. It's not just a game for our factories. It starts with design, integrating the ideas of manufacturing into it. It's embracing new forms of fabrication, not just the traditional. It's having our factories be brilliant, able to collect data and give feedback into our design, to identify the new opportunities, and then to, again, embrace a supply chain that is ever changing. Traditionally, what we've done for growth is have a very linear world. We design our products, we choose our materials, we plan how to manufacture. That worked for decades. It was a wonderful model, but it was slow. It had limited interactions, and it really meant that we put all our risk into the early part, into the design. We spent all our time, all our new tools in the early phases because that made sense. So when we got to materials and manufacturing, we said, let's go low risk. We put all our risk at the beginning. We put out ideas. It limited what we could do. In today's world, powered by software, powered by communication, powered by new ecosystems, we have to work more interactively. This is a new model for how we have to design, how we have to test, how we have to service. New types of interactions, new types of data flow, and that's what we're going to talk about on our panel today. This isn't the same old model. And if we want to grow, if our companies, our institutions, our agencies want to be the leader, this is the catalyst. Innovation is going to grow out of this. It's going to thrive. You know, I'm going to show a movie here, and I'd like to ask H.D. Stevens to narrate just for a moment, because this is what we could imagine.
So what we wanted to show here was the possibility of the future. This is clearly a rendering of a manufacturing pod, if you will, printing an aerospace vehicle. And this is one of the things we do to think about how could we get to a more integrated design and manufacturing scheme that can bring agility to our programs and to our products in order to deliver value for our customers and for our shareholders. So that's a little video there that I wanted to share with you.
Thank you, HD, and I think you put it perfectly. It's to make us think. So over the next hour, folks, think. Think about what you're doing in your organization. Think about the types of interactions you have. Think about what you're embracing. All these new technologies, are you leveraging them to the fullest? Because the challenge is that it's not just one new technology. It's not just one new type of material. It's not just one new type of software. It's a whole system. Starting with design, through the whole supply chain, we need to interact more. We need to be constantly learning. It needs to be alive. So as I mentioned, we have 4 wonderful panelists who, as you'll hear in just a moment, are quite esteemed. They really bring so much experience and energy to this movement, and I know we're gonna have a good time. So from your left to right, I'd like to introduce our panelists. Our first panelist is Tom Williams, and he's the Director of Propulsion Systems Department at the George C. Marshall Space Flight Center. Mr. Williams directs over 400 employees, responsible for providing integrated, quality propulsion products and engineering services to NASA, other government agencies, and the commercial propulsion development community. Mr. Williams comes to the scene with a vast amount of development and operational experience associated with the Space Shuttle, Constellation, and recently with the Space Launch System program currently being developed as a heavy lift vehicle for human space exploration. He's a member of several multi-government agency advisory groups and has won numerous awards, including the NASA Exceptional Achievement Medal, the Center Director's Commendation and Spaceflight Awareness Honoree, and he's completed numerous courses as well as teaching across the country. Just a really recognized person. So join me in welcoming Mr. Williams. Our next panelist you've already heard from, it's H.D. Stevens, and Dr. Stevens is the Director and Chief Engineer for Lockheed Martin Space Technology Advanced Research and Development Laboratories. We have all got to get shorter names for our organizations, mine included. Dr. Stevens is the Development and Transition Key Director, and he impacts space system company lines of business in both the civil and the military spaces, as well as the strategic missile defense system and commercial space applications. He has over 20 years of progressive experience with multiple organizations across the industry. He's a subject matter expert in guidance, navigation, and control, and has major contributions to 5 on-orbit spacecraft. Join me in welcoming Dr. Stevens. Our next panelist is Joaquin Castro. Joaquin is the Space Advanced Program Director for Aerojet Rocketdyne. He has over 35 years of propulsion engineering management and leadership experience, the majority of those years with the Pratt & Whitney Company. With Pratt & Whitney, he was responsible for design, development, and deployment of hypersonic propulsion products, as well as the design, development, certification, vehicle integration, field support, and flight test, the man did a lot, of gas turbine, scramjet, and rocket engines. He's a fellow of AIAA and was inducted into the International Space Hall of Fame in 2013 as a member of the DCX team. Quite a man. Mr. Castro, welcome. Finally, Ed Morris. Ed is the Vice President for the National Center for Defense Manufacturing and Machining and the Director of America Makes. If you haven't heard about this, this is important. The National Additive Manufacturing Innovation Institute. Previously, Mr. Morris was the Director of Mechanical Engineering and Manufacturing for Lockheed Martin as part of their corporate engineering and technology team. He's an active member of the National Defense Industrial Association's Manufacturing Division. And Mr. Morris represents industry on the DoD Mantech Program Strategic Planning Working Group and the Joint Defense Manufacturing Technology Panel's Electronics Subpanel and Advanced Manufacturing Engineering Subpanel. In 2013, Mr. Morris received the Outstanding Aerospace Engineering Award from Purdue University's School of Aeronautics and Astronautics. Ed, welcome. All right, so much going on, wonderful panel of industrial users. And so I'm gonna start the discussion with Ed. Ed, increasingly, additive manufacturing, of now which you're leading America Makes, is playing a bigger role in manufacturing. How do you see industry thinking about it today, and how is it really evolving for the future?
Excellent question. It's evolving rapidly across all business sectors in the United States and globally. There are companies that are early adopters, as usually you see in new technologies. There's companies that are still looking under the hood to decide whether they want to engage, but the adoption of additive manufacturing has been accelerating quite rapidly, particularly over the last 3 or 4 years. Some of the patents on the manufacturing equipment have expired, allowing some low-end additive manufacturing equipment for the maker community. That's growing faster than a wildfire. And the thing that excites me with what's happening with the additive manufacturing equipment, it's reconnecting people that think design with manufacturing. Going back to really what was used to have in the American manufacturing culture, and I'm a little bit different when I talk about manufacturing. When I say manufacturing, I'm talking about big M. It's everything that you do to conceive, design, produce, test, field, support, and ultimately dispose of product. So people think about manufacturing being last. It's first and last and everything in the middle. And additive manufacturing playing a key role to reconnect the design engineer with the actual production process.
Excellent, excellent, Ed. I agree with you. And Tom, now NASA's really starting to embrace additive and think about how that can change what you do. And you know, that's an industry which has had so many breakthroughs, but also by nature has to be conservative. How is a company like NASA thinking about additive and just advanced manufacturing in general?
Well, we're using it to make things faster and make things more affordably. Additive manufacturing is just another tool. It's a revolutionary tool, I think, in the world of materials and manufacturing, where, you know, ceramics, composites, and now additive manufacturing. But every once in a while, an incremental revolutionary approach to manufacturing helps us solve some of the problems that we're really burdened with in making the kind of progress that we need to make with regard to propulsion. So additive manufacturing in combination with some of the other technological tools like structured light, IR imaging for in-process control when we're using the additive manufacturing, as well as the digital design, systems design tools that our analysts have, our stress analysts. It's really enabling our folks to be more innovative and creative around what's possible in the design. So we've used it as an incubator of sorts to gather some of our more innovative, more creative personnel to kind of push the envelope around how can we make things faster and more affordably. And not just from a manufacturing standpoint, but from a complete cycle standpoint. We call it retooling the engineering workforce. So what can we do in design, development, requirements development, test, evaluation, certification? We're looking at ways to compress that time frame. Today it takes a long time and a lot of money to develop a liquid engine system.
Yes.
And so that's one of the impasses that we face with regard to new developments. So we're using the additive manufacturing technology to address not only design and manufacturing, but test, certification, evaluation, the entire process to make us better.
Excellent, excellent. Aerojet Rocketdyne, making some of the most advanced products. You've been engaged for so long with design, with test, and I know you're very passionate about additive manufacturing. When you think about this paradigm of design working more together, the possibilities with additive and many other technologies that now can be connected, how do you think about advanced manufacturing? What does advanced manufacturing mean to you?
Well, in our industry, we're unlike the commercial or automobile industry, or even the airline industry or the aviation industry, where you're making thousands of parts. We make perhaps singles and double-digit numbers of engines a year. Additive manufacturing really has the potential to be a disruptive technology and significantly impact the cost of the hardware that we produce. You tend to think of, okay, you make a part. First of all, you're streamlining the design process. You go from a 3D model into making hardware, and without necessarily making hundreds or dozens of drawings and things of the sort. But also the impact on the ability to bring a significant amount of innovation to the development process, where if you can make a part, and now you're not waiting 6 months or a year lead time to make a part. If you have to make a modification or a change, you go, you learn from tests. Like we like to say, we test a little, we learn a lot. We change the design of the part, and within 2 weeks you have the same part and bring it back to test again. So it's revolutionary not only on the fact that it's specially suited for low volume manufacturing and the ability to do that, but the impact that it will have in the development process and the certification process, not just manufacturing, but in the whole life cycle of a new product, is a revolutionary technology that will significantly change the way we do business and increase the affordability of our products.
Great. Great. I totally agree. HG, you started the discussion by saying we need to think differently. And I think all of us today are trying to figure out how can we be faster, how can we embrace things, but there's things we got to do. You can just mention certification. There's new tools available. When you think about the marriage of tools, ideas, new technologies, we've mentioned additive a lot, but there's many new manufacturing technologies. Really, what is that doing to your expectations as one of the leaders in our industry, and how do we have to work differently?
So it's not only affecting our expectations, it's affecting our business today. And we're rolling out a thought process called the digital tapestry, where we're trying to connect, and we are connecting in major areas, our new business elements, all the way through with that manufacturing with a single digital thread, sharing a common set of models through that whole process. And really what that does is that shrinks the team and brings everybody closer to delivering that product, whatever that product is, to the customer. And we've demonstrated in a couple of different ways the ability to prototype parts, even using a simple MakerBot, polymer, which is a $2,000 desktop kind of device. We've demonstrated initial concepts for flight hardware in a matter of days, and demonstrated those for customers, and then made the sale. And at the end of the day, that's what it's all about.
That's great.
So it's about the digital tapestry in combination with this technology that really, I think, makes it powerful for our business and for our customers.
I love that term, digital tapestry. Tom, how do you think about it?
Well, I'd just like to add to that. We're already seeing in the design process some of the typical interfaces being blurred.
Right.
Okay, where you had a classical design where you had your injector team, and then you had your valve team, and they were all working separately and throwing loads and environments over the fence to each other, where these interfaces are now being blurred, where you can integrally manufacture a complex part like an injector and couple it in one piece, one manufacturing, a set of valve bodies. And so with the modern digital modeling capabilities, you can have that all in one model. You can do a systems, loads, and environments assessment, and you can optimize the design around the system instead of people being beholden, or engineers being beholden to their margins on a particular interface.
So do you think that helps us manage margin at maybe at a higher level?
Yes, absolutely. And I think it's having impacts on the way people look at designs from a team standpoint. They're looking for ways to optimize the system performance and optimize the ability for that system to perform over the ability of their component to perform.
The digital tapestry, blurred design, everyone optimizing. I just think about the workforce today and how we were trained, how we think about it. I mentioned we're going from linear to interactive. Ed, we're putting a lot of the future in your hand with America's Makes, because it's going to take a new type of workforce, and it's going to take integration of some of these skills. And I just admire so much what you're doing. Perhaps can you comment on what the past few moments conversation and tell people a little bit about what you're doing from a workforce point of view?
Sure. I'll begin with a quick comment on the digital tapestry. I will cautiously confess being guilty of coining the phrase.
Well, we all use it, so you were very successful.
Well, thank you. And the basis is I've seen the thread, and the thread is inadequate. You've got to have the tapestry threads of engineering design, engineering analysis, manufacturing modeling simulation, training for the users, et cetera. Then you've got not only the OEM tap threads, you've got the supply chain, you've got the support crew. It really is a tapestry in the coming generations of business in America.
Excellent, excellent points. I agree.
Regarding training and education, in the space of additive manufacturing, certainly America Makes, the National Additive Manufacturing Innovation Institute, is chartered to train in the principles and use of additive manufacturing, or 3D printing, as everybody really calls it. We've been approached by a lot of folks that are energetic in the training business, wanting to train technicians on how to run the equipment, and that's important, but that's not really the major barrier to get to the tipping point of ubiquitous use of additive manufacturing in the United States. The significant educational barrier is training engineers to work in this new space. It's different. So we are pushing the envelope on how do we educate the current workforce and the oncoming workforce on how to embrace and really do the designs. You had in one of your pictures the bracket that you did at General Electric with a competition. You probably couldn't tell from the photograph. You could see it was pretty artistic. It had a lot of holes in it and so forth, but it was actually hollow. But it wasn't cast hollow, it was printed to be hollow, optimizing the strength and taking out the weight. That's a whole new design concept for those of us who are trained in XYZ orthogonal engineering versus artistic. So I'm a champion of STEAM, science, technology, engineering, art, and mathematics, because it takes that artistic thought process in what you're doing. But pushing the envelope further on the impact that additive manufacturing and 3D printing, I think, is going to have, especially in the United States, if we do the things that we're doing. An aha moment for us was not only can you teach 3D printing and additive manufacturing, but you can use 3D printing or additive manufacturing to teach. You can make STEM fun. You can make the new culture come on board. If they think it, they can design it, they can make it, and they can actually do it at home. I've got Brent Lambert was the Manufacturing Industrial Base Policy Director in Office of Secretary of Defense. Had the girls were twins, our twins, they were 9 years old at the time that he bought them a 3D printer. And it changed their lifestyle with their friends. Now, instead of just playing games, etc., they would meet Saturday morning, design jewelry, make the jewelry, and sell it to their friends on Monday morning in school.
It's amazing.
They're learning design, manufacturing, and business. That's a whole new paradigm of culture.
8 years old.
It's exciting in what's happening.
And you bring up great points. You know, this is our next generation workforce, and every one of us in this room has a responsibility to both embrace it and as well as to champion it. Now, Joaquin, as part of your role, you know, you had strategy and business development for Aerojet Rocketdyne, and as you're thinking about your next gen products, how does this whole concept of advanced manufacturing, more integrated, when you think about product development, how's that playing a part now?
Well, it plays a key role. I'm proud to say that Aerojet Rocketdyne is actually a leader in the industry. We've now, for a number of years, had a totally digital factory. As a matter of fact, every one of our technicians, every one of our mechanics are issued a company laptop. All of our work instructions are electronic. We can actually transfer models from the design process into the manufacturing and assembly process. This is all digital, it's paperless. So we've been doing that already. The same thing applies to our supply chain. We can digitally transfer back and forth with our vendors and make the parts. Goes back again to the idea of, as you mentioned, you generate a design. Let's think of something, for example, a piece that requires some flow. So you go and you make an SLA part, you conduct a water test, you take that same design, tweak it, now you take that same model and evolves into a part that you can actually go run in an engine. I'll give you as an example, we are developing a very low-cost engine family. We call it Bantam. We designed and manufactured and totally printed a liquid rocket engine. The design and manufacture took less than 4 months. And we ran it. We ran an engine where we actually took even some of the critical dimensional features without doing any additional machining, and successfully ran the engine, proved our performance. The only things we machined where the flange interface is between the three components.
Sure.
So we've actually printed without having to go back and, like the example that Greg showed this morning, the technician was actually trimming the parts with, no, we took the parts as they came and we ran them as an engine. And we're proceeding, maturing that technology, so we're bringing the automated factory, we're bringing including additive manufacturing and some of the other features as we discussed into our products. We're in the process of leveraging this technology for our production engines, with the goal, again, as I mentioned in my earlier comment, to significantly impact the affordability of the parts.
Wow.
Our customers at NASA and the DoD and commercial customers keep demanding lower cost, but with the same level of mission assurance and quality. And additive manufacturing, and some of the other attributes as a digital factory and things of the sort, are key factors in getting there.
That's great. That's great.
So one of the factors to add to that is the opportunity for this capability to change our culture from a risk adverse kind of a culture. There was a panel this morning discussing how do we sustain ourselves in an industry where there's a dearth or a paucity of hardware. Well, we're seeing orders of magnitude reductions in costs, and for complex parts where you would normally spend 12 to 18 months long lead items down to weeks and a couple months. And so what that provides for a designer and a developer, the ability to take more risk, because if you've got more parts, if you fail a part, or if you learn something during a test, you can make another one more readily, and you're not so worried about failing at the test stand. In the past, when it took 12 to 18 months and a lot of analysis to make sure you didn't fail when you finally got the test. So a lot of this has got the opportunity to change the risk-averse culture that we're all struggling with as managers to push through.
So Tom, I love that discussion, thank you, because it is about changing a culture. It's about working differently, and we've heard many examples over the last 40 minutes or so. HD, you're a thought leader in this area, just embracing change and thinking about more optimized design. We've talked about a lot of great opportunities, but I think there's a lot of gaps too. When you think about changing a culture, risk, new way of working, what do you see today as some of the gaps at Lockheed Martin as representative of the whole industry? Because we all feel it.
Well, so and sitting in the seat as a prime, working with our government customers and with our commercial customers, they're looking out and they need a highly reliable system that's going to be functional over that 15 or 20 years in the space environment. We have spacecraft today that have been orbiting Mars for 15 years. So you take a step back and think about this. Let me go back to another example. Hubble Space Telescope's been on orbit for 24 years.
Excellent point.
Think about that for a moment. And that was designed then like 30, 35 years ago. So the lifespan of our products are extensive. So as we move from, we're flying today an additive aircam titanium part on the Juno mission that's on its way to Jupiter right now. And it's a secondary structure, a little bit of a demonstration of the possible. And as we now move from the art of the possible into bringing additive into the mainstream, which, as we've talked about, has benefits for our business, we're really looking at, okay, how do I make sure, how do I certify, how do I qualify that process? And it really looks a lot like a couple examples that we've done in the past where we've introduced a new shuttle tank, a new material for the shuttle tank, and flew it 4 years later. When we started introducing composite parts, we had a similar kind of culture clash with, wow, how do I analyze these things? And what do I do with them? I feel like we're facing a lot of the same things. So here I go to a customer who's very conservative and their system has to work, and they want to know what are the risks, what are the failure modes, and that's what we have to focus on is, what are the risks, what are the failure modes, how do we mitigate those? And so we're working through those. Right now, we're taking a machine by machine kind of approach to work with our customers and bring this into the mainstream of our business.
That's great. That's great. And again, I think that's part of the culture.
Can I pick up on that? Because it's a key process. We've sat here for the last 20, 30 minutes, and we alluded to the great attributes of this disruptive technology that really has the ability to change our world. But there are some illities that go along with the technology, and I think it's as important to discuss what those potential shortfalls are as it is of all the positive attributes. And when I talk about illities, there's two that come to mind, actually three. Portability, inspectability. Portability is, as you mentioned, there's a proliferation of machines out there. You go out and you have to develop very clear processes, and you have to document how you make these parts on the machine. The quality of your, for the sake of argument, let's talk about SLM, your powder, if you're using a power system. How you maintain that power, how you keep it, the traceability where that came from, its proper constituency and chemistry is extremely important. Just because you develop one process for one machine manufacturer doesn't mean that those set of parameters and settings apply to the others. So you have to be, in our case, we have our own machines, we have a supply chain that has different machines. We have to be very sensitive how we translate from one machine to the other one.
Correct.
The other one is inspectability. Very easy through a number of technologies to inspect the outer dimensions of the part, but the technology gives us a unique capability to create very intricate, hidden passages. In the traditional manufacturing process, you would make those, you will inspect, and you would weld the cover on it, and you have clearly, and it's not as easy to do that in a part that is totally enclosed when it comes out of the machine. The other thing that is extremely challenging is there's many folks out there making parts, and there's some beautiful parts. But at least in the aerospace industry, just a beautiful part doesn't cut it. You have to have had a design system. You have to have statistical properties database. You have to understand the designs. One of the gentlemen mentioned that you don't design, just like you don't design a composite part the way you design a metallic part, you don't necessarily design an AM part the way you did a subtracted manufacturing part. You take advantage of some of the attributes. You have to take things into account like support and things of the sort. And last is how do you qualify these parts? Because some of the issues that I mentioned, and it's no difference, fit, form, function, just like whether you make a part through a normal manufacturing process or not. But it's extremely expensive, especially in the aerospace business, to qualify new hardware. So the point of introduction of the technology into the production process is not only driven by the affordability of the actual part, but also the accessibility to a good point in time to create a qualification and prove it that it works.
You're exactly right, and you know that's where I talk about program agility. Why I talk about that, because it's not only about the affordability of the part, but also time to market, ability to respond to changes in requirements, whatever those come from. That's kind of embodied in that whole agility, and that's part of the business case that has to close. But part of that business case is also the cost and time associated with qualification, certification, and one of the challenges that I've had is getting people to think about this more like a composite part and less like a metallic part.
Excellent, I think.
Yeah, so I want my A basis numbers. Well, that's not the way we're doing this.
And you have the great opportunity to talk to more partners than probably all of us combined, industry, public, private, universities, national labs. And, we just had a discussion around some of the great challenges that we're all willing to take on, but they are challenges. What's your perspective, and what are you hearing? What do you think various roles can be for all of us to play?
Sure. These technical challenges and barriers and roadblocks actually get to the fundamental of why America exists as a National Lab Manufacturing Innovation Institute. And we've pulled together the public and private partners and done some extensive road mapping that we keep current, which is challenging as rapid as technology is changing, on what needs to be done next in research and development. Interestingly enough, in another couple of weeks, we will be 2 years old. And the magic of a public-private partnership is combining the federal funds with private industry and academia to address these issues in a very scientific, methodical approach. So at the moment, we have a portfolio of over $35 million of research and development underway, over 22 projects, addressing various aspects of these barriers that need to be solved to get to a ubiquitous use in our product portfolios and drive the U.S. economy in a very positive way. So we're investing in materials, allowables, and databases. We're investing in process control in process, controlling the temperature, the melt speeds, et cetera, et cetera, et cetera. We're investing in how you do design to minimize the post-processing that's actually required.
Yeah.
We've got projects that are taking place on extensive projects, some of us funded by NIST, on how do you do the non-destructive inspection, evaluation, and so forth. And some really fascinating projects in other areas of endeavor. One of the projects is how you do the optimization of mechanical and electronic 3D printed parts. Another one that is fascinating to me in the medical community that we're supporting, but it has interesting ramifications in other applications. If you use a implant structure while bone is regrowing that's made out of a magnesium alloy, the magnesium is bioreabsorbable. And by the time the bone grows back, the support structure can be gone and you don't have to do surgery to remove it.
Wow.
That's pretty cool.
So those are some of the things in our investment
Fascinating.
portfolio to knock these issues down, leveraging the combined federal money with the private money in academia to accelerate the solutions so these gentlemen can put it to work.
Fascinating. I love that, and congratulations on 2 years. And I think we all have a responsibility to learn about this and play our role. Tom, what do you think has to happen next as we look at embracing change? We're introducing new materials, new processes. We've talked a lot about additive, but there's a whole wealth out there, new ways of machining and drilling and bringing these people together. I loved your comment around changing a culture. What are some of the next steps, do you think? Then I'll ask all my panelists to comment on what are some of the next steps as we move forward of integrating design, manufacturing, and materials.
Well, I think we need to continue the energy and keep the drive behind the creativity and the innovation. I think Joaquin and HD touched on the illities. And I really, when I talk about design, development, test, evaluation, verification, validation, and certification, it really does touch on all of those. And so we need to put a focus, as Ed says, into materials properties, I should say, and look at the opportunities that additive provides us in the way of inspectability with digital tools like CT scan, where you can get internal dimensions of a part coupled with structured white light scanning, that you can get the OD dimensions of these parts. These are all digital tools that make things faster and more reliable. That feed your analytical models. There are other opportunities with additive too. I mean, if you can build two parts, proof test one, and use the other, that's an option that's available to us today that may not have been available to us in the past. You can build essentially tag-end dog bones or material property specimens alongside your actual part. So you've got material properties of the as-built part that make it less critical to have possibly a basis. So those are some of the things that we're starting to look at now, in addition to building parts that you can test more rapidly, more readily, get more iterations. You can thicken the parts where your high stress areas are. So all those are opportunities that now our designers, developers are looking at to get to certification with the same amount of pedigree, integrity that we have with the old methods.
Perfect. HC, what do you think needs to happen next?
Well, there's a couple of things that were mentioned here, but I wanted to pick up on one. I still think we have a ways to go in terms of getting what I would call aerospace quality machines on the market today. We're getting there, but building in, I would like to see inspection as a post-processing step eliminated. Yeah. You do it as part of your manufacturing process, and it goes with. So that's really how you're going to get the cost out, is by cutting out entire steps and entire portions of your process. So having in situ inspection that goes right along with your manufacturing process, I think is one thing that I know we're looking for in the future. I'm hoping through, America Makes or some other entity, we can actually come together and decide on some standards for, how we decide how good is good enough when we're going to try and certify something, and what method we want to use. Historically, we have done that through forums like this meeting here. So I think there's opportunities for this kind of an organization to get involved in that, standard setting. And then the other thing is really driving engagement in our workforce, and that's bringing the group together. It's a much tighter integration between the guy who's touching the part and the guy who's designing the part, and the person who's the new business person who's envisioning what this system might actually do for a customer. And so as we basically shrink that whole process and then align it with a set of common models, there's still a lot of work to be done to make that digital tapestry into reality. I think we're taking some great steps in places, but there's other places that have much work to be done.
Excellent points. Excellent.
Look,
Yuki?
I can't disagree with any of the things that Tom or HD said. I would add a couple of things. I think the standards are somewhat driven by the industry. I don't think you're going to get a set of standards. I think the automotive, the commercial industry would have a standard that perhaps will not be as demanding as aerospace or the nuclear industry or things of the sort. So I think we will continue to leverage the electronic tapestry, the electronic factory, whatever terminology you want to call it, into evolving more and more automation into our processes and our manufacturing. Specifically, when it comes to additive manufacturing, two things that I'd like to see in the future evolve is machines that are capable of producing larger parts. We're already moving from the traditional 9-inch to a 15 by 19-inch. Some of my large rocket engine injectors, which are specifically suited for additive manufacturing because of the intricate geometry inside the injector, the post that supports the fuel and the oxidizer domes and the injector ports, for some of the larger engines are very big. An R68 is about 18, 20 inches in diameter. SSME is as big. So we'd like to continue to see the technology expand to be able to handle larger scale hardware so we can bring that automation. We have been working very, very hard internally on our own material-based database of property. So we're progressing there. Most of the work, because it's the easiest thing to do, has been done in static hardware. But as we migrate, we want to apply this technology to rotating hardware as well. I love that film that was shown this morning, the little Angel Bell jet engine that GE built. The structural demands for a rotating piece of hardware that may turn 20, 30, 40,000 RPM are significantly high. Not the databases, not just on yield and strength and whatnot, but fracture mechanics and void size and the detection methods that are required for that. So it's a significant leap in addition to what we've done for static hardware to move on into the rotating hardware, and it's demanding. So that and larger sizes are things that I think should be driving us to expand the applicability of the technology in the future.
Great. Ed, what has happened next?
One of the issues that we find ourselves dealing with frequently, particularly with the media, even with members of Congress, the hype. There's a lot of hype with additive manufacturing. And we're trying to bring a voice of reason and reality to what you can and cannot do with additive manufacturing. If you give a young kid a hammer, suddenly everything looks like a nail, and you have holes where you don't want them. It's not a hammer that hits everything. It's just another tool in the toolbox, albeit a very, very powerful tool because it does different things, different capabilities. In the future factory, I've absolutely taken for granted we will see a growth of machines that do a combination of additive and subtractive machine work processes on the same machine. But we need to make sure we're understanding what additive manufacturing is best at and then what traditional manufacturing is best at and sort that out. And I think that's a fundamental thing where we're at. The hype can get us in more trouble than we want.
Good point.
Excellent, excellent. In just a moment, I'm going to open up for questions from the audience, so be thinking of the cool questions you have out there. I'd just like to throw a question out to our panel for anyone to answer. We've talked about tools, integration, machines. One of the things we haven't touched on too much is, organizationally, how do we need to think about the difference in advanced manufacturing? We've touched on it slightly, just talking about, designers working more and integrating. That's not a natural act. It's not a natural act because of how we've all been taught and the way we have our processes and our structures. I'd love to hear if anyone's starting to address that with their team.
Because I lived through that. 30 years ago, as a mechanical design engineer, I would make the design, and typically we would involve a manufacturing rep at the final design review, and he or she would come and say, but those tolerances are too tight. Well, my machine can only do this. And our answer back then was, get a better machine. Okay. Well, that drove expense and cost into the hardware. The world has changed. At least in my company today, we work in what we call integrated product teams. From the kickoff of a project, when we review the progress and on a weekly basis, we have a team that encompasses not just designers and structural people and heat transfer folks, but manufacturing representatives are there day to day with us today. Excellent. Again, not to focus necessarily on additive manufacturing, but also as we begin to bring more of that technology into our product lines, there's a new set of skills, and those folks are in there with us every day and maturing the design, getting ready and helping transition the idea from, not from paper now, from electrons into the factory. So by the application implementation of integrated product teams, I think we're addressing that and making the manufacturing folks an integral, important part of a design team, which is what we need to do. So that's how we address it.
Let me share a perspective on that. And speaking at the national manufacturing level in any industry where manufacturers involved, they get big in manufacturing. I've been concerned for some time about the separation of the design engineer and the factory floor. With offshoring, with thin integrators, et cetera, used to be in my early engineering days, I could walk down to the factory floor and get that feedback. Now we're in an environment in business in the United States, manufacturing business in the United States, where it's lucky if the engineer knows what factory it's actually built in or what country it's built in, so that feedback is not there. And I'll directly suggest that the feedback from the shop floor, from the production operations, is the fertilizer of future innovation. And we starve that fertilizer, that feedback, the tolerance, knowledge, and so forth, we are losing our manufacturing design edge. And by reconnecting it with integrated process teams, putting 3D printers on the engineering floor, right beside their desks, starts to reintegrate it, getting that feedback, fertilizer into the DNA of future designs. That'll change the design significantly in the United States and make us more productive. New products, new innovations, more affordability, and deal with all these abilities.
So I'm going to pick up on that and say, it's happening for us in a bottoms-up kind of way. So where the maker world, Maker Faire is a big deal in the Bay Area. So quite frankly, the first MakerBot was brought in by one of our engineers saying, hey, this thing is going to be cool. And and for a couple $1,000s, leadership was like, okay, we'll try it. And it's made a huge impact, and it's really brought the teams together in that integrated product team manner. We were doing a design for a yet-to-be-released product, and the team went out and used a series of MakerBots and some simple things, and in a week, prototyped the entire setup, demonstrated it. Now, it only ran like 4 or 5 times before parts broke because it wasn't designed to do that. But they were able, again, make that demonstration to a customer, make the sale. And quite frankly, the manufacturing guys had a lot of ideas for the designers about, well, if you did it this way, you could do this. And so now you see that in this design that we'll be rolling out in the next couple of years. So, it's already having an impact today.
Mm-hmm. I think it's having a natural impact on the organizational structure, whether we like it or not. I mentioned the blurring of the lines between interfaces, and so now you've got engineers that are, we're encouraging to become multidisciplined engineers that can do more than one thing. And so you can get smaller teams gathered around a system model, and they spend more of their day looking at the system and how to optimize it and to change their particular part to make the whole system work. So it's had a natural systems integration effect on our organization. And of course, a lot of the organizations in a traditional sense are made up based on classical interfaces. So that's one way it's having a big effect on the way we organize.
Well, I know just hearing from these experts in the industry, I've got a number of questions to continue, but before I continue, I'd like to open up. Any questions from the audience at this time? If you could go to one of the mics, we have 2 in each aisle, and if it is directed to one of the panelists, please do so. Yes. If you could also announce your name and your organization, that'd be wonderful.
I'm Ann Clausen with Alcoa, and I had a question directed to any or all of the panelists. Okay. And it has to do with Me Too syndrome. You know, I think when we all walked around the exhibition hall, I think pretty much every single table either mentioned additive manufacturing or had samples on display. Mm-hmm. And are there situations where it really doesn't make sense for a company currently in some sort of aerospace manufacturing to be entering into additive processes? You know, are there newer entrants where it's worth making that investment, worth developing that expertise, or are there situations where that can actually hurt them? Because I feel like everyone's being pressured to do something with additive. They don't know what. They just want to be part of the party, you know?
The cool kids
so
are doing it, right?
All right, thank you.
I totally disagree with that characterization. I think additive, as I mentioned, is a disruptive technology. In my lifetime in this business, the only other disruptive technology, and I don't work electronics, so I'm going to leave that, that's a different world, is CFD analysis and the ability to do, to model the Euler equations and understand flow the way we do today with CFD. That, at least in my lifetime, those are 2 things that have significantly make a difference. I don't think, at least in my environment, in my company, we're not being pressured. We saw the technology, we saw people using it, and we said, God, that's going to make a difference. Our customers keep demanding lower cost. And in a low volume business like ours, where we make 6, 12, 20 engines a year, with the complex, intricate shapes that we have to make with the significant demands and structurally and thermally that we do, it's heaven-sent technology, okay? Now, if I'm making 100,000 widgets a year, rather than having 3,000 machines making 100,000 widgets, once I develop the part, I may invest in good hard tooling, and maybe I'll do casting or forging or NC machining or you name it. You find the best tool that gives you the best product for the price. So at least in my perspective, I don't think we're being pushed or we're Me Too. We just saw something that had tremendous potential and embarked it with full vigor.
I guess I want to articulate that a little differently. It's about the right tool for the right job.
Right.
And so I would advise anybody to go out and get some level of understanding of what this technology can do, and then evaluate the business case for your particular business and your product line. Because as I mentioned before, it's about bringing agility, costs, time to market, ability to respond to changes in requirements. That's really how it impacts our business.
Exactly.
And so understanding what the technology can do and then understanding how it impacts your business is the integral part to, does the business case for machine X or machine Y or this category make sense? So it's still got to be rooted in a business case.
And today, the biggest impacts are relative to the more complex parts. So the more complex, the longer the lead for classical manufacturing techniques there are associated with that part, the bigger the benefits there are for additive. But the simpler the part, then more classical manufacturing techniques are still probably the best way to do those.
We've got a very patient gentleman there.
If I may, I think every business owes it to themselves and their owners and stockholders to at least understand and look at the technology. If you look at the early roots of 3D printing, additive manufacturing, it was for rapid prototyping, called rapid prototyping. So you still can do prototyping. You can do functional prototyping. You can do tooling.
tooling is a huge impact.
Right now, the F-35 is built using 5,000 tools made from 3D printing.
Correct.
Wow.
5,000 tools.
That's
And then you can
wonderful
do
statistic.
end items and assemblies and so forth. Let me flip the way you think about that. As I engage with universities across the United States, some of them have approached us with some eagerness and excitement, saying that they are going to start a bachelor's or a master's or a degree in additive manufacturing. And I look at them in all sincerity and politeness and say, please don't do that. Take additive manufacturing 3D printing and embed it in all of your course curricula.
Correct.
Put it in all of your engineering, mechanical, electrical, et cetera, put it in your materials design, put it in your medical school, put it in your legal school, put it in your business school. Everybody needs to understand what this does and can do, and then go with it from there. It's going to be a wild ride. We have yet to imagine what you can do.
Can I add a comment to that? I am a member of the advisory board to the Mechanical and Aerospace Engineering School at University of Florida. They got an SLA machine, and they were having tremendous amount of difficulty with affordability and making parts for the wind tunnels that were testing cascade vanes, okay? The kids got together, they designed it, they made plastic parts. They've included in their curriculum. It's not additive manufacturing, it's part of the aerodynamic course.
Perfect.
They've made it perfect. They have parts that are durable, they can change geometries, they can learn the effects. It's been a fantastic tool for education.
Excellent, excellent. Yes, sir.
This question is primarily for Mr. Williams, but I'd like everybody on the panel to give their industry perspective of it if they could. When you talk about additive manufacturing, there's some things it can't do. One of those is, in our environment, change the legal environment that we're currently in. The laws won't change if you're looking at FAA or JANAF certification, those types of things. That's kind of an inflexible model that was designed for the monolithic waterfall development of times past, not really adapted to additive manufacturing. How do you suggest we modernize that in the future and get to a place where if you change the placement of a screw, you don't have to go back to step one and requalify everything?
Yeah, that's a good question. I think from a NASA perspective, we lead. You know, we fly human-rated systems, and you know, the standards and the specifications and the certification processes we own. You know, with organizations that have independence and have technical oversight for that, but you have to pull them into the conversation around how do we do this better, and help them allow us to think of ways to get to the same place that we want to from a certification standpoint with more innovative, creative ways, and in some ways more robust situations. So I think the governing bodies you have to pull in at some point when it comes time to certify or inspect. Your quality organizations, your safety and mission assurance organizations have to be part of this conversation and the solutions that you eventually evolve to. And as we have successes and as we learn the lessons and as we fly more parts, it's just like any other technology that has a hard time finding its way in. It's got to work its way into the system, and it takes leadership, and it takes energy, and it takes you know, a need to get us there. And I think the need is the cost and the schedule that it takes to design, develop, test, and certify the current systems that we're dealing with today. It takes too long, and it costs too much. So the imperative is there for all of us to try to figure out how to make this technology benefit the United States, industry, government, and the country from the goals and endeavors that we're trying to achieve.
So I just want to pick up on that. It requires engagement by everybody, and really understanding the assumptions that went into the current requirements, because they're usually it's in the assumptions. There are certain assumptions that were around when that process was written, and you're changing those assumptions. And so really kind of makes you go back and have that conversation about what's really important here. And you know, keep it focused at what's really important here and what are the assumptions that went in and how are we changing those, and then how do we adapt our certification. And that's how we were able to, you know, fly a new material for a shuttle tank in 4 years.
So you're saying it could be an opportunity
I look at it as an
as
opportunity.
opposed to a barrier right now to go back and look. That's a great point.
Let me come at it from a different way. I don't think why we would identify additive manufacturing in something different from metal matrix composites or any of the other manufacturing technologies or new materials that come to play. Yeah, there are things we need to do about inspectability and things we already talked about, but it all comes to a piece of hardware of form, fit, and function. Through whatever attributes, we have to prove that the part, if you're replacing a part with a new part, it meets the same form, fit, and function, or is better. And the same certification and approval methods that we have in place where the part is made through a casting, through a forging, through additive manufacturing, or you bring in some composites, they all apply. Don't think of this as something new. If anything else, the electronic fiber, or digital fiber as you coin it, because of the ease of exchange of information, the capability of bringing everybody to work together, may make that process a little simpler. But it's no different how you make the widget. The widget still has to do what it's supposed to do, and you have to prove that it works.
Yep.
So just a little bit deeper perspective, it's already well articulated in terms of the criticality of specs and standards, and having the specs and standards catch up with the technology. It's a given that we're not caught up in that area. I'm a firm believer in modeling simulation. Certainly in my days in the business, huge strides in modeling simulation. And of course, to do man-rated systems, the fidelity has to be extraordinary. And I don't think we're there yet in many areas of manufacturing, modeling, and simulation. However, we've been partnering with our friends at the Department of Energy, and particularly the folks that are in the nuclear community. And we've had some fascinating conversations in their perspective. I got this problem, Ed. I can't test. I have to model and simulate. So they're doing high-performance computing and pushing the edge on the fidelity of their computer capabilities. And we need to go in that direction. Now, is it going to solve all the problems? I doubt it. But it's the right direction to go.
Okay. Thank you. Thank you. Yes, we'll take one last question.
Steve Millard here, FAA. I got a question for the panel in general. It seems like you know, one of your goals is to reduce the schedules and the costs associated with manufacturing, because you know one of the big things is making everything more affordable. And I guess, you know, in my thinking, you know, if we're going to achieve the next order of magnitude developments in the space exploration and space utilization, it seems to me like one of the key things that's got to happen is you start, you know, not doing all your manufacturing and everything here on, you know, planet Earth, but you know, actually getting into the area where you start doing manufacturing and testing and stuff like that in space. You know, because that's where you can really, you know, you're not contained by volume and mass as you are here on Earth. So, what are those kind of thoughts getting to the cradle? Are people starting to think about that, develop that, think about those kind of ideas, and you know, trying to really move us forward to the next order of magnitude, you know, space development and utilization?
Well, I suspect almost everybody in this room knows that my public partners, NASA, are about to put a 3D printer on the space station. And I've heard within the last several days that they're accelerating the launch date of that. Pretty exciting stuff. There's pretty fascinating technical issues in terms of outgassing and so forth to be dealt with. But it's clearly in the plan of what do we do in space. We've also been discussions about what do we use with the moon dust as a material to print, et cetera. Pretty exciting times of where this might go.
So certainly in my circles, we're talking about, you know, how do you, when you talk about Orion, how do you send a vehicle on a long duration space flight and potentially have to repair that vehicle, or, you know, you've got the Apollo 13 scenario. Well, now if you start thinking about how does a printer fit into that, and it fits in very well. So that kind of scenario is certainly under discussion. I think our friends at NASA who are, you know, doing this first step in that direction with a polymer printer, I believe. We'll see how that goes, and they've got some lessons to teach us all, I'm sure. Yes. But when you start pulling that thread, you very quickly see that it's going to be a major impact as we take humans primarily beyond low Earth orbit.
I guess the only comment I would make, you still have to live through the laws of physics. You may have a significant reduction in volume, but you still need to get the raw material mass up there.
Correct.
So it's,
Correct.
Physics still rules.
Correct.
Usually does. Usually does. Yes, last question.
Hi, my name's John Thomas. I'm the past president of the International Council on Systems Engineering and a professional systems engineer. You know, it occurs to me that for decades, the systems design process and systems engineers have thought about this thing as a constantly decomposable thing until finally you get down to a part that needs to be made. And when that part's there, historically, already the functions have been allocated to it, and that's kind of a constraint. I'm starting to sense that this adaptive manufacturing actually is going to start poking at what functions do you want to be able to put in a part in which the assumption was that you couldn't manufacture that in that construct as well. What do you see as far as for shaking up the systems thinking community on how they need to work closely with your organizations?
Well, I guess I want to give an example as a response to that. And I'll go back to this mechanism that I talked about earlier that we prototyped and demonstrated in a couple weeks. We had the system engineers, the designers, the manufacturing folks working together. They did 3 iterations on that in a period of about 2 weeks. And so there you got to, the system engineer had some idea or had some thought about how to decompose that problem. They worked on it, prototyped it, figured out some things, learned some things, and then went and did it again and did it again. So that's sort of, and I hate to use the buzzword spiral development, but that's kind of what it sort of looks like. Is in fact, you're educating essentially up and down that decomposition and modifying it as you're going.
I think it gets to the blurring the lines comment as well. You're able to build more functions into one component. And so that has a lot of benefits. Yeah, it has drawbacks too. I mean, if you have a failure in a proof test or something, then you've got more manufacturing time and effort into it. But if you combine 3 functions into one part, then you can do acceptance testing on one part. So you have to do those trades from a systems level to decide what makes the most sense. And it depends on the system too. If you're looking at a Eclipse system or a propulsion system, or you need the systems engineers in the room kind of leading that activity and doing the what if kind of questions to drive the designers to where we've got a better system.
Let me begin by saying I'm a champion of systems engineering. I get it, understand the value. We're actually using systems engineering approach in our road mapping. However, in my career, I've had the opportunity to see the discipline of systems engineering evolve, and from what I saw, it started from preliminary design engineers. They were all systems engineers. My current perspective is every engineer has to be a systems engineer.
Agreed.
And to believe that there is systems engineer and then other engineers is wrong thinking, bad thinking. Everyone has to be a systems engineer. To your point, I have in my hand a lightweight polymer roller bearing. It was not assembled, it was printed. So if I set aside overly constrained systems engineering, and I think about what I might do this inner race that holds the balls that were, again, printed, not assembled, could be primary structure. And I could print the ball and outer race around it. System engineer that is not thinking at that detailed level, but a system engineer that is doing that design might take a systems engineering approach and do some integration that you would not have thought of otherwise in the breakdown of the functions to parts.
Great. Well, I think you'll agree with me. The way we work, the products we can make, the types of skill sets we need, we're really on the verge of the next industrial revolution. And I hope that today's session made all of you think about how you're engaging. I've got to tell you, when I say honored, that's an understatement. I've been honored to have these gentlemen on the panel. They've taught me a ton. They are leaders in their industry, thought leaders, and join me in a round of applause for our panelists. I'd also like to thank AIAA for inviting us. We're all quite thrilled to be talking about this. This is a passionate subject. We're all just starting. Welcome to the revolution, and thank you for being a part.
Thank you.
Thank you.